Thank you so much. And it's really, really great to see so many people here. It's a little bit of a surprise, actually. I've been at a couple of these type of events around Stockholm and so on. I think this is sort of twice the size, basically, two times as many people. Exactly. And as you've noticed, I'm from Stockholm. I work on the East Coast. And the first thing I'm going to do, I'm going to try to keep you on your toes, probably by being completely incoherent, because my 3-year-old daughter has what I guess would be described as vinterkräksjukan. What is that in English? Winter throwing up disease. It sounds terrible. So I haven't slept for a very long time. Let's see how much sense this actually makes. But we're going to try anyway. And I have a few jobs, basically. So yes, I'm involved in the Wallenberg Autonomous Systems program, the AI part of it. My main job is to be a manager for one of the research laboratories within the Swedish Institute of Computer Science, called the Decisions, Networks and Analytics. We're basically the AI laboratory of SIX, the Swedish Institute of Computer Science. We're like 40, 45 people. I also coordinate the rest of the people at SIX that do machine learning and analytics and so on. So perhaps in total around 50 researchers or something like that. Now, I need to tell you sort of what we are, I guess, as well, when it says RISE here, because nowadays we're not just the Swedish Institute of Computer Science, we're also part of Research Institutes of Sweden, which is all kinds of research institutes merging into one. So I come from an organization that was like 200 people. Now we're part of an organization that's like 2,600 people or something like that. And AI is everywhere there, and I have the happy job of trying to coordinate all of that work. So that's also one of my jobs. It's a great challenge, but it's also a great opportunity because we work with so many applications and so many different types of data. So, right, I'm going to talk a little bit about how to build really large-scale learning machines that sort of, well, I looked at the invitation and it said Gothenburg AI Initiative or something like that. And I thought, yeah, let's talk a little bit about how to move beyond just machine learning towards cognitive systems. And as I already said, I'm a little bit tired, so it's going to be an interesting talk about moving towards full cognitive systems by basically failing cognitive system. But let's try to keep things under control. And I think by now I'm just going to actually expose myself and say that I'm not only perhaps incoherent, but I'm also going to say that I'm actually pretty darn old. I've been doing machine learning for more than 20 years. And I actually had a talk with one of the other organizers of this event earlier this morning, and I realized something, that we started doing neural networks in the late 90s. I did that as an undergraduate and also at the Swedish Institute of Computer Science. And we were writing these algorithms that everyone is using now, basically, these backpropagation. Everyone's doing gradient descent. It was never really working all that well. We couldn't really scale up the models. Convergence took forever and so on. So I actually sort of looked up what we were running on. So do you remember Silicon Graphics, Ultra Sparks, that kind of workstation and stuff like that? I think we were running at around 10 to 100 megaflops, million floating point operations per second. Now I have access to the Wallenberg architecture, and we can run on many, what are they called? NVIDIA V100s or something like that, GPUs, which run at between, depending on how you count, I looked it up, 10 to 100 teraflops. So that's 1,000,000 times faster. No wonder that we can do stuff today with these gradient descent methods that we could never do just 20 years ago, basically. We got nowhere. However, also referring back to an earlier presentation, while deep learning is super important, it's super important for lots of different applications that we do at SIX. It's super important for the picture of AI and what you can do with machine learning and so on, it is just another classifier. It is just function approximation. And of course, I'm not gonna argue with Karpati and say that, you know, it's nothing more than function approximation. Yes, it's so much more. It's a different way of approaching programming and how to build systems, basically. Absolutely. We exchange basically our input and coding time towards data, which is great. But what we're typically doing with deep neural networks is function approximation. And this is extremely useful for many, many, many things. But it's not really everything we need to build something that we call artificial intelligence. But we can use them for some things. So what are some of the good things about these deep neural networks? First of all, of course, they make for, if you have enough data, excellent predictors, classifiers, what have you. But they also provide a way for us to abstract away some detail. We can move away from pixels to more abstract concepts and things like that. We can move away from sound samples to actual significant phrases and things like that, if we actually train these things the right way. So let's have a look at that. I'm also going to talk a little bit more about actual history and so on, because as I said, we've been working with this for at least 20 years. The laboratory that I'm now heading was actually called Neural Networks and Real-Time Computation when I started working there. Then, of course, these things never really worked, so we switched name and now we're back again. But when did we actually really see the really big resurgence in interest? Well, that was actually around 2015, when sort of at the same time when we got better than human performance on certain object identification tasks and stuff like that within machine learning. That, combined with a few other events, really sparked a huge amount of interest. So it's really good that we have this interest. It's also a little bit worrying, because what we can do with these systems, it's a lot. What people think we can do with these systems, especially when you have very little data and things like that, is very often not quite matching with reality. So what are we going to do to fix that, basically? So let's have a look at another very cool thing that we can actually do. Sort of a secret thing. This is actually the training data. But we can actually just combine, for example, image data and text data, and from a picture, train a classifier, so to speak, or a predictive model to predict a descriptive text based just on the image. This actually works. Does it know anything about the resulting model? Does it know anything about what's in the pictures, how they relate to other things? Can it reason about it or something like that? No, not at all. It's still very much pattern recognition. That is still what we're doing. And this comes with problems. We had an excellent talk earlier today about reinforcement learning. Reinforcement learning is super interesting because it brings us somewhat closer to build actual, real artificial intelligence systems that interact with the world and can actually start to at least somewhat reason about the world themselves. But they are still pretty limited. I mean, if we go back a few years, everyone's seen this paper about Google learning to play, DeepMind learning to play Atari games. Yeah, in this case, it works pretty well, at least for the games that are not depending a lot on, let's say, long-term strategy and things like that. If it's just short control loops and things like that, yeah, we can learn them. Actually reasoning about the game, understanding the game, and building strategies is still incredibly important and very difficult. So how do we fix that, basically? In a sense, and I know this has been said a lot of times, and but I still think the analogy sort of works. We can sort of look at deep learning and some other machine learning techniques, actually, as sort of the new steam engine. It's really powerful. It's really new, as if we compare to when steam engines started coming into industrial production and can perform work that is well, basically the fundamentals of a revolution. But it's not entirely efficient. It needs a lot of resources. It's not deployable anywhere. You can't, these things were big. The same sort of goes for machine learning today. It's not that easy to move it around, actually. I'll give some more examples later. And I know that Neil Lawrence and others have actually made the analogy that actually deep learning today is an early form of steam engines that were really inefficient, that you could even not put on trains and things like that, but you could only use in sort of mines and things like that. Then they got better, and this is sort of what we need to fix with deep learning and machine learning itself. Another thing that sort of works with this analogy is that machine learning or deep learning, yeah, it's a really, really powerful steam engine, but it's not necessarily a, let's say you want to build a transportation system. It's not a transportation system. That consists of a whole lot more. And the analogy sort of works for machine learning and AI here as well. AI is a whole lot more than just this learning part. So if you, for some reason, I know most of you here are not academics necessarily, but if you, for some reason, we're going to write an application for funding, research funding, within machine learning or AI, these points have been valid for the last few years. They're still valid today. These are major research directions that we're working to fix, basically. The first one is basically that machine learning is not very interpretable and sometimes lacks usability of results, basically. One of the problems is it's difficult to get timely results in many cases, especially when you want to not just do inference, but also do online training at the same time. We always have the problem of correlation versus causation. And actually finding causal relationships from data is, as I imagine that you know, incredibly hard. There are methods, they scale terribly, and they don't work all that well in practice. We're trying to look into some of these algorithms, but it's very, very difficult to get them to work in practice. Not necessarily the most important part for building human-like intelligence, to be perfectly honest, as humans are pretty bad at just from raw data determine causation. But for many of the applications that we're looking at, this is essential. The final two is perhaps the most importantly mentioned ones. We need a measure of uncertainty, and I think this was discussed earlier today as well, basically. So one approach to actually determining trust in models and things like that is for them to tell you how uncertain they are of a result. So instead of just predicting a point estimate, you, for example, predict a distribution. That tells you, am I very, very certain that there's a cat in this picture, or am I incredibly uncertain? This is incredibly important, very, very difficult to do in practice. And the final point that always is recurring is explainable models, breaking up the black box of, for example, deep neural networks. This is difficult to do, possibly doable in at least limited senses and so on, but I'm going to argue here today that perhaps a more usable road in the long term is to create interactable models. Models of the world that we can learn, that we can actually, as humans or other learning machines, interact with and actually ask for explanations and bases and so on. So that's a different way forward. Another really, really important point is that machine learning still lacks in efficiency. First of all, it lacks efficiency in terms of data. We have worked for a very long time to learn from very small data sets. It's very difficult to do so. And I think if you've tried to do machine learning in practice, you already know that actually good data is difficult to come by. You don't always have it. I think the first real clash with reality I had was many years ago when we were actually tasked to build an interactive diagnostic systems for actually Swedish defense. And of course, we were machine learning people. We approached it as a machine learning person would. Let's find the data, let's train something, in this case actually neural network model, and then deploy it. However, when we were asking for the data, we of course realized that for many of the diagnostic cases, there is absolutely no data at all. This has never happened, but it's still something you would like to diagnose. Then moving into medicine, you come into the same scenario again and again and again. There's actually no example data. And this is actually quite common in practice. So we need to handle these cases, basically. Now, for this kind of system, we actually did so. It's efficient, and it's not very efficient in terms of computation and development time. That's a systems aspect, and we'll discuss that a little bit. Let's move on to what drives our machine learning research, basically, because we as a research institute want to actually implement things like this in real life. And our basic goal is to expand the environment for machine learning. The current practice of actually just viewing machine learning as taking something that typically is some either structured data, like a table or something like that, train something on it and then deploy it on something with the same kind of data records fed into, that's very rarely the case. The platforms are decentralized, they're distributed, we need to put machine learning everywhere. The data sources are very restricted and they come and go. They don't exist for a very long time and they don't exactly represent exactly the same data. It's difficult to interact with machine learning models and we need to get way better at it. And perhaps more fundamentally, we don't really know what we're doing when we're actually building machine learning systems. We're just trying out things and hoping that they work. So there are still very many fundamentals to actually research and deal with. So how do we deal with privacy trade-offs? How do we deal with the fundamental limits of learning? And what are they? So that we can actually say something about these systems before we actually build them. And we work within most of these things. We work in uncertainty modeling, both for example, Gaussian processes and neural networks, and actually also different types of random forests. We work on interpretive models and things like that, deriving causal relations, and we have quite a lot of research funding to do that. We apply this in all kinds of areas. We do things for, I'm sure that if you were from example, Volvo or things like that, we have worked with you, for example, on visual analytics or perhaps fuel consumption prediction and stuff like that. And we do this all over, basically. But this is not necessarily what I'm here to talk about today. I'm going to talk about how to move from machine learning towards more AI. And AI is not necessarily a term that I actually really like. I sort of prefer the terms machine intelligence, or actually what we're doing today is closer to cybernetics than artificial intelligence. But at least artificial intelligence conjures up something that is, triggers the imagination of people. So perhaps it's really useful. But we've been working on it for a really long time. This is the first mention of artificial intelligence that I know of, a summer conference in 1955, and the people behind it are actually fantastic. McCarthy, Minsky, and Shannon, they did some amazing work. And we actually have seen recent successes within things that we would sort of call AI. For example, everyone has studied the DeepMind results on playing Go, AlphaGo and AlphaZero and things like that. Reasoning terms really come in there. They're not just using at all deep neural networks for predicting things. They're also using, for example, Monte Carlo tree search to search the whole solution space and things like that. And this is an incredibly important component. However, it's still an incredibly limited type of reasoning, basically. And if we go back to actually labeling or producing text based on images and so on, this is something that I actually picked up from from a paper a couple of years ago. So this is what happens when you just train a model on that and then apply it to pictures. Here you can actually see that there is actually really no reasoning. There's no anomaly detection. There's nothing like that involved. So the middle picture there is an airplane is parked on the tarmac at an airport. Yeah, well, you can sort of see why it would say that. It's sort of an airplane. That could be the tarmac at an airport, but it sort of misses the essential point of the image, which is really not about being parked at a tarmac at an airport. The same goes for a man riding a motorcycle on a beach. I think that sort of also misses the central point of that picture. And the same thing, a group of people standing on top of a beach sort of downplays the actual drama of the picture. And this is essentially just because we're just doing pattern recognition. We're just doing, in a sense, function approximation, which is super important, but very limited. So let's take a look at what we need to do to move further, basically. So if you have read Kahneman's Thinking Fast and Slow, he talks about two systems. System one, which is the intuitive system, the one that you just react with, and so on. The thing that we basically do today, the system that is just pattern recognition. He also talks about system two, which is actually when we sit down and think about things, when we reason about things, and we can actually use that kind of reasoning to learn. So what I'm telling you here today is basically that we can do so much within system one today. We need to study and develop how to build and learn representations that work as system two. So this is my central message, basically, my take-home message. And this is what we are focusing on if we are talking about algorithm research, moving beyond deep learning. And how do we do that? Well, basically, we talk about reasoning about concepts, abstract concepts, and trying to learn representations of abstract concepts that we can perform computation on. We also want to some kind of set of operations that we can perform on these things. For example, we want to say that we want to be able to ask if the concept yellow is sort of a part of entails to the concept color, and so on. We want to reason with analogies, saying, for example, the classical example, I guess, is man and woman relate to each other as king and queen, if you've read Mikolov's papers. Using such primitives, we can actually build the foundation of a reasoning system that we can ask general questions to. More than that, we can possibly inject knowledge in a way more efficient sense. So if we can actually construct these operations and these representations, if we can actually tell the machine that yes, yellow is a color, that constitutes the equivalence of a huge number of examples, basically. So let's build such a machine. So how do we do that? Well, after going back and forth about lots of basic representations and how do these things look like and things like that, we've actually sort of started to take a real engineering approach. Let's try to build it, basically. Let's try to build such a system, see what happens. And here we've divided things into perception, reasoning, and interaction. What I've been talking about today is that machine learning typically does is perception. Feature extraction, anomaly detection, prediction, all that kind of things. But essentially, we can use it to lift our abstraction level. Then we have the reasoning part, which we also want to learn from data as much as possible. And then interaction. Interaction is still difficult. We do it in incredibly crude ways, but we're focusing on the reasoning part, basically. How do we build this? I'm going to show you in a while what our basic approach is, but I'm also going to mention that what we sort of envision is a little step beyond current computational platforms. So at the same time, we're running tons of projects focusing on how do we build computational platforms that supports this. And one of these things we're doing is building a complete system architecture for AI, basically. One of the things that we wanted to do is to be able to scale between and trade off not just resources, number of computers and so on, and time, like you would do in a data center, but actually uncertainty. It's very, very rare that you only that you need perfect precision of an answer. You can often trade when you want to make a decision, for example, calculation times towards uncertainty. So how do we build systems that support that? Well, basically, we want to build a declarative programming language so that we don't have to worry too much about the details. And this is important because we need to move between different platforms and representations and so on. That can combine the typical stuff that we express ourselves in, relational algebra, graph processing, linear algebra, and so on. And essentially, we want to be able to define progress metrics, because that is what we can use to, for example, measure this uncertainty. These need to run on one intermediate language. We don't want to switch representations. It takes too much time. And it needs to work on a full distributed runtime on lots of different platforms. So how far have we gotten? Well, we're building the distributed runtime right now. But we have a financing for this for 5 years. So we're going to get there in the end, basically. Let's move back to this picture. Now we looked at a little bit about the supporting platform, basically. Now, how do we build this part? We've already talked about the perception part, which is sort of like the peripheral nervous system. Now we want to build a central nervous system. We sort of looked at something that is relatively, let's say, continuous and distributed, and we want to move to something that is more discrete concepts that we can actually work with. And our basic approach is that everything is defined by interaction. Everything is essentially defined by how it interacts with everything else. And essentially that means that everything is defined by correlation, how things correlate to each other. This is a basic assumption, for example, within language modeling. But if we want to extend this beyond just, for example, words, we want to extend it to the representations, top representations in neural networks representing images, people and other entities and so on, we need to be able to reason about this on an actually massive scale. So this was the work we started doing a couple of years ago. Can we actually do that? And the core concept here is similarity. So we have a number of objects. Let's start from the beginning. We have a number of objects. These can be people, words, proteins, system states, whatever, basically. They have correlations or interactions. It's, who is friend with who? Does this co-occur with something else? Does it interact with something else? So what is similarity? Well, we start again with the basis for almost all modern natural language processing. You shall know a word by the company it keeps. We move to you should know an object by the company it keeps. Everything is defined by the company it keeps. So let's look at that. We have an object. It relates to some other objects. We call these objects the context. And then the basic assumption is that similar objects have similar contexts. Similar objects are exchangeable. And that really means something. And a typical way of actually measuring this is, for example, to do this on correlations using the, for example, cosine measure or something like that. Here on these calculations, we use an normalized L1 measure. It's almost equivalent. It simplifies calculations. So basically, we use to make this scalable that similar objects are one neighbor apart. They're not further apart than that in the graph, basically. So we can compare edges to shared neighbors. We transform this whole thing into a two-hop graph, into a graph that consists of basically like these things, and then perform the transformation. And what it sort of looks like is this. If you have a correlation graph, these things are correlated. A weighted graph, now this is just 1 and 0. We transform this to a similarity graph. Right. Now this is not TensorFlow or anything like that. This is actually, I think, pseudocode, or is it actually, yeah, this is actually Spark code. This is the whole thing, basically. It's way faster than the n square operation that we typically would have to use. It sort of runs in n log n time on all realistic data. So this is incredibly fast. So what do we get if we look at text and words co-occurring with each other in a sort of context? Well, we get exactly like this. Words cluster together. Welterweight, heavyweight, middleweight together. Eastbound, southbound, westbound, northbound together. And once we have this graph, we can actually run simple, scalable clustering algorithms on it and detect clusters of interchangeable objects. These basically constitute higher order concepts that we also can use for reasoning. So eastbound, southbound, westbound, northbound, yeah, that's directions, right? So we can actually take a step back. These ones represent, let's say, OR concepts. One or the other, they're interchangeable. And start from the beginning and start building higher order concepts. We can do the same thing in the correlation graph and see that white and house typically occur together, and those should be grouped together. So, does this work? Yeah, sure it does. This is done on Spotify data. Yeah, it's really easy to just look at how people listen to music and actually find out different genres, basically, because people listen to different genres. I'm not even going to go into this because this is made by a colleague of mine, and I don't know the biology field, but yeah, this sort of typically works pretty well. I understand. We can run it on just complete Wikipedia and actually detect most of the topics and clusters within Wikipedia. We can run it on, we did that after listening to some talks about Facebook and how there were no real filter bubbles and things like that. Yeah, so we had a look. These are users. Yeah, this looks like something horrible in a Petri dish or something like that. These are actually similar users grouped. It's very, very blotty. It's very, very much groups grouped together. The same actually goes for hashtags. It's a bit smoothed out, but people actually look at hashtags really, really grouped together, basically. But let's look at one of the absolute fundamental problems with just looking at this, for example, at text or in just the context of songs or something like that. So if you use these methods to just define what is a banana, you usually get something like this. It's an eatable tropical fruit, because no one writes that bananas are yellow. That's sort of understood, right? Everyone knows that. No one describes that in text. So what is the cure for that? And that is multimodality. We already heard a little bit about that, grounding concepts in different modes of data, basically. Because if we can actually look at text and pictures of bananas together, we'll realize that actually, yes, bananas are typically yellow. So multimodality is absolutely essential. That is what's going to drive our research the next few years. We can already do some cool things with it. This is using actually a deep neural network to lift the abstraction layer level and then combined with text group things. And yes, you can actually see that it produces, if you could actually read what it says, you could actually see that it produces usable concepts. Interesting with this kind of research is that actual fundamentals really, really start to matter. How we measure correlation, for example, becomes incredibly important, because in all of this data, especially when trying to build higher order concepts, data always becomes sparse. We always have concepts and so on with very few examples, or co-occurrences with very, very few examples. So how do we deal with that? Well, we basically need to find a new way to measure correlation. And there can be a good argument made that mutual information, Shannon's mutual information, is actually an incredibly good general correlation measure. And in this case, for a lot of the stuff that we do, point-wise mutual information, basically measuring the correlation just between different events. So how do we actually approach this problem? Well, we start from Bayesian statistics and make a prior assumption about the distributions, look at the data, and predict not just a point estimate on the correlation, but actually the full distribution. If we know the full distribution, then we can make a measure that is way more conservative and way more useful in practice, basically. Does it work? Yeah, I'm really not going to go through the results here, but as standard nowadays in machine learning, you need some bold numbers for your methods in your graphs. Yeah, those are there. It becomes better than all other correlation measures. The most important thing is what happens when you get to way small text sizes and sizes of data, basically. It still sort of works where the traditional methods of pointwise mutual information completely breaks down. There is absolutely nothing left. So actually, looking at really, really large-scale building learning machines that can reason about things triggers us to actually work on really, really basic problems. And this is sort of a teaser about another such extremely basic problem that we're currently, well, actually, we have sort of solved it, but we haven't published it yet, so I'm not going to show you the details of it. So this is a bit of a teaser, basically. So this is sort of an illustration of an ion channel. These are sort of the transistors of the human brain and so on. So why is actually the human brain still important? Well, neural networks, the way we use them nowadays, are perhaps not a super great representation of actual neurons and how the brain works, but they can sort of, as I said, represent the peripheral nervous system. What we want to do is to represent memory in the central nervous system, computing with concepts. And why is biology still important? Well, it provides us with an existence proof. So if we can look at that and see what is actually possible to do, that sort of puts us as a baseline. If we can do this, we should be able to do most of these things. And this is what we have actually done. We have defined a method to derive completely new representations, actually representing conceptual spaces. Not just point estimates, but conceptual spaces. We can reason about entailment. Is this a more general entity than that one? We can do way better reasoning around analogy. We can possibly do different types of counterfactual reasoning and stuff like that, which is super interesting. Is this more computationally intense than using the traditional methods that I sort of described earlier? Yes, way more. But within a computer with, for example, 1 terabyte of RAM, you can at least keep 500,000 concepts or something like that and actually compute upon them. And as I said, I'm not going to actually tell you exactly how we do it because this is sort of being published right now. But if you would like to have a look at sort of the basis of what we're trying to do and where we're coming from, you can look at, for example, Järnfors's Conceptual Spaces from 2000, very good book on how to reason with this. You can have a look at my former colleague, Pentti Kanerva's Hyperdimensional Computing from 2009, which describes very much the same kind of approach. And also, as I mentioned earlier, Kahneman Thinking Fast and Slow provides a good reference, basically, for the field. So I'm just going to skip to the final slide, basically. What I want to sort of make clear for everyone here today is that, first of all, and you all know that, AI is so much more than machine learning. And to build something that actually represents something that, let's say, the general public thinks of as artificial intelligence, we need to bring in so many more things. There is so much more to rediscover. We have sort of been touching these concepts for a very, very long time. I believe that reasoning systems or computing with concepts is basically the key to solving a lot of issues. Lack of data, explainability, interaction, and more general AI that can answer more general questions, basically. The fundamental representations for this is still an open research question. We have a suggestion, but it's still an open question. It's not necessarily just deep neural networks, although they are very, very important. Wide data, multimodality, and looking at way different types of data modes is essential to actually build something, even a proof of concept, that really works in practice. And finally, systems and platforms do matter. Right now, it's difficult for us even to perform some of these experiments because, I mean, we're working with 1 terabyte representations. They don't fit on any GPU or anything like that. So how do we actually manage them? Systems and platforms really do matter, but we're going to develop them in conjunction with this during the next few years. And with that, I'm going to say thank you. And I know that it's late in the day, but I think we might have time for a couple of questions or something like that.